Topic 2.7 is about VSEPR theory and bond hybridization. So the objective for this topic is based on the relationship between Lewis diagrams, VSEPR theory, bond orders, and bond polarities. So pulling multiple things together, you're going to explain structural properties of molecules and explain the electron properties of the molecules. So this is where we're really getting into the higher level of the shapes and what the electrons are, what's happening with the electron orbitals when covalent bonding happens. So let's start with VSEPR theory. Okay, I pronounce it VSEPR theory. Some people say it's VSEPR, however you want to pronounce it, whatever. I say it's VSEPR. Yes, I know the vowel's in the wrong spot. Anyway, VSEPR theory, valence shell electron pair repulsion theory. It's a lot of words, but let's look at this. Okay, so valence shell electrons, bonding electrons, they're the only electrons we've really been talking about when we're talking about bonding. Okay, so that part's fine. Valence shell electron. Pair repulsion. So this is where we're remembering that electrons have like charges, and like charges don't like to be next to each other. Okay, so they're happy with two together, they'll form a bond, but that's about their limit. So pairs of electrons or bonds are going to repel each other, and they're going to want to be as far apart as possible in 3D. So this is where we're going to make the stretch from a two-dimensional Lewis drawing to a three-dimensional shape based on where the electrons are and what bonding is happening. So there's actually a table that we're going to look at, and I'm going to move my little camera off to the side so you can see the whole thing. Okay, VSEPR theory all depends on how many things are connected to a central atom. And I say things because it's not necessarily other atoms. It's atoms or lone pairs, okay? So it's the number of things connected to the center. And it comes down to 6 main categories. So if you have a central atom with 2 things, it's linear. There's only one option because linear things are, so if it's linear, it's not going to have any lone pairs because then it's not 2 things on the central atom. So if there's a central atom and then 2 others, it's always linear. If there's 3 things, so 2 atoms and 1 lone pair of electrons, there we go, it's going to be trigonal, planar, if it's 3 atoms, bent, if it's 3 atoms and 1 lone pair of electrons. So we use 2 different names. Tetrahedral is if there's a central atom with 4 things. So it's tetrahedral if there's a central atom and 4 atoms connected. It's trigonal pyramidal if it's 3 atoms, 1 lone pair of electrons. And then it's also bent if it's 2 lone pairs and 2 atoms. So you can get the bent shape 2 ways. Okay, you can get the bent shape by having 2 atoms, 2 lone pairs, or 2 atoms, 1 lone pair. Either way, if there's 2 atoms connected to the center with some amount with either 2 or 1 lone pairs of electrons, it's going to be bent. Okay, trigonal pyramidal, I like to think of it as it's tetrahedral, but with the top one pulled off. Okay, so it's still standing up. It's not flat like trigonal planar is. It's still standing up like a pyramid, but there's just 3 of them instead of 4 like a typical pyramid would have. Okay, if there's a central atom and 5 things, 5 atoms is trigonal bipyramidal. So basically there are 2 of them. There's the top one and there's the bottom one. If there's 4 atoms and 1 lone pair of electrons, it's seesaw, or this particular graph does sawhorse. So, okay, you got to get a little creative with this one, but tip your head off to the side. So it's got the 2 angled pieces standing up like this, and then it's got the 2 straight pieces out. You got to think a little creatively, but it looks kind of like a seesaw that you might see at an old school playground. I haven't seen a seesaw in a really long time, but you got to get a little creative with that visual. Or you can just memorize it, central atom with 4 outside atoms, 1 lone pair, seesaw shaped. T-shaped is 1 central, 3 outside atoms, 2 lone pairs of electrons. So again, this one, the picture is a little hard to imagine. I am terrible at visualizing things in 3 dimensions. If you're good at it, congratulations. Some things in life are going to be a lot easier for you. I'm really bad at it. So you have to think a little creatively with this one, but they're all in the same plane. All the connected atoms are, and then their two lone pairs are going to be out to the outside. So they're going to be in the same plane and they're going to make a T shape. And then you can also get linear, which are your top two atoms, and then all the ones around the center are lone pairs of electrons, because those bonding, all of this comes from those bonding electrons are going to want to get as far apart from each other as possible, along taking into account the lone pairs. And then the last one is a central atom with 6 things around the outside. If it's 6 atoms, it's octahedral. If it's, oh my gosh, I just totally lost my train of thought. That's really dumb. I'm reading a chart. Next one is square pyramidal. So if you have a central atom and 5 things on the outside and 1 lone pair, square pyramidal. Square planar is 4 atoms around your central atom and 2 lone pairs of electrons. So again, they're all in the same plane and they make a square. They actually make kind of a diamond, but a square. T-shaped is the same as the T-shaped from the 5 terminal things, except in this case, it's got 3 lone pairs of electrons instead of just 2, but it gives you the same shape. They're all in the same plane. There's the 2 top, and then there's the 1 coming out. And then this one also forms a linear shape. So if you have a central atom with 2 atoms on the top and bottom, and then electrons around the center. So when I think about my 5 and 6 level shapes, so the top 2 are always going to stay there. Your top 2 atoms are always going to stay there. And then you're going to start picking the ones off in the middle and adding in lone pairs. So that's shape-wise, that's where your lone pairs are going to go. So sometimes I think that helps visualize what the shape might be. A lot of this comes from practice. Again, some of it comes down to just how good are you at visualizing what's going on with these atoms and these molecules, and comparing a 2-dimensional versus a 3-dimensional shape. If you're better at memorizing things, you can just straight up memorize it because there is a pattern to it. Whatever works for you. We will be doing some practice though, and I'll try to give you as many tips and suggestions as I can as we work through how to visualize these things. But let's talk about the last piece for this, which is bond order. I'm going to move my little camera again so it's out of the way. Bond order was mentioned kind of just without the name in resonance. So it's the average of each individual bond order. So individual bond order is really easy. If it's single, it's 1, double is 2, triple is 3. So if you're looking at the overall bond order of a molecule, it's the average of all the bonds around your central atom. So if you have a central atom that has a single bond and a double bond off of it, you add the 1 plus the 2, divide it by 2, you get 1.5. Okay, so you're looking at what that average is of all the bonds. That's what we look at when we look at overall bond order. Okay, bond hybridization. So when we talk about bond hybridization, we're going to use a different theory. It's called valence bond theory. This is really similar to Lewis and our Lewis structures, and so we're going to kind of use those to guide our bond hybridization. And so this goes a little bit deeper, and it acknowledges that the bonds are formed when atomic orbitals overlap. And so we're talking about our S, P, D, and F shapes overlapping here. And so that's how we form bonds, is those shapes overlap. It's like, well, when an S overlaps with an S, that's easy. But what happens when an S overlaps with a P? Okay, so that's where we get hybrid. Okay, so that's where we get kind of blends of the S and the P together, and we call those hybrid orbitals. And those hybrid orbitals that get formed are based on the electron pair geometry or the shape. I'm going to move my little camera again. Okay, so this picture comes out of your textbook, figure 9.3. So it gives you some examples of how we can look at this. So anything that is, so linear shapes are going to have SP hybridization. If we're looking at 3 electron pairs, so 3 things attached, it's going to be sp2. If you're looking at 4 electron pairs or 4 things attached, you're looking at sp3. Here's how I figure this out, okay? And I don't get that deep into it, but this was kind of my shortcut that I don't know, I cannot remember at this point if I was taught it or came up with it, whatever. If you add up the superscripts on your letters, so you're always going to have sp something. You could have more. We're not going to talk about more. but you're going to add them up, and that tells you the number of things that are connected to your central atom. Okay, so a linear has two things, so it's S, which is 1, P, which is 1, 1 plus 1 gets you 2. If it's three things, you have a central atom, three things attached, you're going to have S, 1, P, 2, 2 plus 1 gets you 3. Four things attached, you're going to start, you get 1 S, we have 3 P's, so there's 3 and 1, that gets me 4. Now, if you keep going, you can have sp3d, sp3d2, sp3d3, and you can keep going if you get into more complex, but we're not going to worry about those. But what we're looking at is how those bonds overlap and how they form these hybrid bonds between the atoms. Move my camera again. Okay. So when they form hybrid bonds, they actually don't just form standard covalent bonds. They actually form what are called sigma and pi bonds. Sigma bonds are when the overlap is along the axis of the bond. So those are single bonds. Single bonds are always always sigma bonds. Single, sigma. Easy to remember. If it's a single bond, it's a sigma bond. Pi bonds form when the overlap is above or below that axis between the two atoms. So you're always going to have a sigma bond. You can't have a pi without a sigma. So that center one has already been accounted for. So if you have more overlap either above or below, so that happens when you get double and triple bonds, those are pi bonds. So if you have a single bond, it's sigma. That's it. If you have a double bond, you have one sigma bond, you have one pi bond. If you have a triple bond, you have one sigma bond and you have two pi bonds. Okay, you see how these add up? So the first one is always sigma, the other ones are the pi bonds. The sigma bonds are always stronger than the pi bonds. Those are those first ones. It's because they're along the axis. The pi bonds prevent the rotation of the bond. So they kind of lock it in, and that's part of what makes those triple bonds stronger and shorter than single bonds, is they prevent the rotation. But the sigma bonds are the ones that are stronger. They're the ones that are going to hold on first. So if you're talking about breaking bonds, you're going to break the pi bonds and then you'll break the sigma bond last. So the sigma is always the first, your second, and then possibly your third ones are always your pi bonds. It's a lot of vocabulary. It's a lot of terminology. And so the importance here is being able to keep everything straight. So when we're talking about hybridization, we're talking about sp, sp2, sp3. We're talking about sigma, and we're talking about pi bonds. And it's really just you're drawing your regular Lewis structure, you're thinking about VSEPR theory, and then you're pulling it all together to look at how all of these electrons are going to interact. The point of all of this is no matter what, we're trying to represent something that we have a really hard time representing. Okay, so we're using multiple theories, we're using multiple methods to look at and try to figure out a way to actually represent these bonds and these structures that are way more complex than we can represent in a typical two-dimensional static way. So these are the best ways that we can combine all these little bits and pieces to come up with the closest, best representation that we possibly can.